Hello class, this is the video and the last one for chapter 5, 5.8. We will talk about exponential growth and decay models. I would also just mention for your information, Newton's law, logistic growth, and then decay models, but we'll not do it the examples. Okay. Now, here are the learning objectives. We'll look at the model population that obey the law of what? Uninhibited growth, and then that obey the uninhibited word decay. And like I said, I will mention for your information for the Newton's law of cooling, and then also logistic word model. Okay, so here is the law of uninhibited growth or decay model. It follows this, it is a exponential function, all right, which is a, it is what a of t, that is a function of t, where a naught times e raised to k kt. All right, the a naught, that is the a naught is when the time is what? 0. So it is called the initial amount. Okay, initial amount or original amount. And then k is not equal to, when k is equal to positive, then it is growing. It's an increasing function. When k is negative, it is what? Is a decreasing function. Now, the k is called the what? The k has a special name. It's called the rate. K is what? The growth, either the growth, okay, or decay rate. All right. If it is positive, if k is positive, it is what? It's a growth rate constant, if you want to call that, or it's a decay rate constant. All right. So, and this is the graph when k is positive. So it depends on k, is an exponential function. When k is positive, it's an increasing function, and that is the when t is equal to 0, the initial amount. Okay. And then the same way, if k is negative, it's an exponential decay, and it's what? It's a decreasing function. All right. So we want to look at the uninhibited growth of cells. Okay. There's a model that gives the number, that is a capital N, of cells in a culture, that is in a ecological, in ecology, or in a colony. All right. That after a time t passed is given by what? This function. Because it is growth, it is growing, that is why the k is what? Is positive. Okay. Now it follows the model we just know, which is a naught e raised to what? K times what? T. So in this case, my a of t is your n of t. That takes amount after time t. Okay. All right. And then the n naught is the initial number of cells or initial amount. Okay. So here's an example. It's a colony of bacteria. You know, bacteria grows. It grows very, very quick. Okay. According to the law of inhibited word growth, is given by this function here. N is measured in what? In grams, and T is what? In days. Okay. Determine the initial amount of the bacteria. Okay. That means that what is A naught? That's a question. What is the growth rate? In this case, what is what? What is our K? Okay. What's the growth rate of the bacteria? Okay. And then what is the population after what? After T, after 7 days. That is what is N of what? Of 7 days. What is that going to be? Okay. How long will it take for the population to reach this? Okay. 250 grams. What that means that when your N, what is T, so that this is what? 250. And so we'll take this equation, set it to 250, and then solve for T. So here we'll be looking for what? The T. And then what is the time? That was the doubling time for what? For the population. Doubling time. So here again, you want to find T when your N of T is what? Twice of the initial amount. Okay. So let's take them individual. First, the initial amount we are given this model. if you compare this to the n of t, n of t is what? N naught e raised to what? K t. Now you notice that the n naught is your what? Is the initial amount. So if you compare this to the given function, all right, it is going to be this value here. But that's why we have what? 90 grams. Okay. So we can substitute t into the function. All right. If you substitute t into the function, you get 90, and this is 0 times 0 times times 0.06 is what? 1. So you get e raised to what? E raised to 0. And of course, e raised to 0 is equal to 1. So therefore, we have what? 90 times what? Times 1, which is what? 90 grams. That's why we have that. Or if you compare that, okay, like I said, if you compare this, the n of t is equal to 90 e 0.06 t. If you compare this with what? N of what? N of t, the general what function, which is what? N of 0 e raised to what? K t. Okay, you notice that if you compare that, then your n of the initial amount must equal to what? 90 grams. Okay. So, and then B, the B, what is the what? What is the K? Okay, what is K? All right, what is K? Now, if you compare this to that, you notice that your K will be equal to what? The 0.06, and then it's a percentage. Okay, so you always express it as a percentage. So in this case, if I compare my K, the K is equal to 0.06, or it is what? 6%. Okay, it's all 6%. All right. And then the population after what? 7 days. Population after 7 days. So what's happening is that your T is equal to what? 7 days. We want to substitute that into the function. So we want to evaluate the function at what? At 7, which is what? 90 e raised to 0.06 times what? 7. Okay. And then, oh, I just put it there. Let me erase that, because I typed it, but I forgot that I typed it. All right. So this is equal to what? 90 raised to the 0.06 times what? 7. And if you evaluate this, you get 136.96 what? In 6 grams. Okay, so that's part C. Now let's go to part D. I said to find how long it takes for the population to reach 250. As I said, we solve, okay, we want to find T, okay, when it reaches what? The population reaches what? 250. Because the number of bacteria is increasing. It's an increasing function. That's why the K is positive. All right. So we solve this equation. That is, we have N of T, N of T is what? 90 e raised to 0.06 times T. Excuse me. So if we equate this to what? 250, then we solve for what? We solve for T. Excuse me, let me drink water. All right. Okay. So we want to find a time when the population reaches 250 what? Grams. So we set this to 250 and solve for what? So we have what? 90 e raised to 0.06 times T is equal to 250. Okay. Then we divide both sides by 90. Okay. Then you have what? E raised to 0.06 T is equal to 25 over what? 9, because the zeros will cancel. Please don't evaluate this and run it to any decimal place at this point. Don't do that. because when you do that, it affects your what your results very, very greatly. All right. So since we have what e raised to that, if you want to solve for t, what do? We take what? Take natural log, okay, on both sides. Take natural log on both what? Both sides. Why? Because of the base is e. If I had like 10 raised to 0.0 t equal to 250, in that case, I would take the what? Because the base, I would take the common log on both sides. So take note of that. Okay, so we take natural log of what? E raised to what? 0.06 t is equal to natural log of 25 over what? 9, or 250 over 90. Okay, but I can cross out that. That's why I did that. Then one of the properties, or you have this, the 0 point now comes to the front. So that becomes 0.06 t. Natural log of E is equal to natural log of what? 25 over what? Over 9. Okay. Now, but natural log of E is equal to 1. Okay. Natural log of E is equal to 1. Therefore, we have for 0.06 t is equal to natural log of what? 25 over what? Over 9. Okay. Then we divide both sides by what? By 0.06. So you have 0.06 t divided by 0.06 is equal to natural log of 25 over 9 divided by 0.06. And then when you approximate it, it's equal to what? 17.0 what? Days. 17.0 days. All right. So now it means that the population reaches 250 grams in about what? 17 days. That's what it means. Okay. Now, this part E. It said the population doubles. Remember, we want to find that the population doubles when we have for it 180 grams, so that the doubling time is found by what? Solving the equation. Okay. It said the population doubles when we have what? 180 what grams. So it means that N is equal to, now don't forget your N of T is still what? 90 e raised to what? 0.06 what? 0.06 T. So again, we want to find T. In this case, what is T when it doubles? The initial value is what? Okay, if it doubles, that's the key. Initial value amount is what? 90. So if it doubles, that'll be what? 180 grams. So we set this and solve. So divide both sides by what? By 90. Divide this side by what? By 90. Okay. Then you have what? You got 2 is equal to E raised to what? 0.06 T. All right. Again, take natural log on both sides. You have what? Natural log of 2 is equal to natural log of E, 0.06 T. And the right-hand side becomes 0.06 T, natural log of E, and then natural log of what? 2. Again, natural log of E is equal to 1 because the base is what? The base is what? E. Then divide both sides by, so this becomes 0.06 T is equal to natural log of E. 2. Then divide both sides 0.06, 0.06. All right. So then your T is what? It's equal to natural log of 2. Okay. Divided by what? 0.006. Okay. And what does that give us? Okay. So that is equal to 11.55 approximately. All right. And then that means that the population doubles every what? Every 11.55 days. Okay. So that is what we got that. All right. Now, let's go to example 2, population. It's a colony of bacteria increases according to the law of what? Inhibited growth. If n is the number of cells and t is the time in hours, okay, take note of that, in hours, express n as a function of what? As a function of t. B, if the number of bacteria doubles in 5 hours, find the function that gives the number of cells in the culture. Okay, so here our goal is to find what the k is. All right, because we have the initial, which is the n. So what is k? And this will still be there. All right. How long will it take for the size of the colony to triple? Okay. So this will be triple. That's 3 times. In other words, n of t is equal to 3 times what? The initial amount. Okay. So then D, how long will it take for the population to double a second time? Okay. That is why it's increased by 4 times. So in this case, your n of t is equal to 4 times the initial. So 2 times that doubles, triples, and quadruple, and so on. All right. So here is the solution A. We want to find the function, express what n as a function of what t, when n is the number of cells. Okay, so using the formula that we just talked about, all right, here you now have what? N of t is equal to n of 0. That's initial e raised to what? K times t. So that is our function, which is right there. So where n is not is initial a number of what? Bacteria in the colony or present, and k is the positive what? Number. So here your k is positive because it's growing, it's increasing. Okay, B. Now we have for a function as a function of, we don't know k, so we need to determine what a k is. Therefore, it says that if the number of bacteria doubles in 5 hours, all right, find the function that gives the number of cells in the culture. Okay, in 5 hours, it means that when t is equal to 5, all right, we want to know what a k, if t is equal to 5, the n of t, that is n of t is equal to 2 times the what? The initial amount. So we can find that then. So the question is, what is what? What is the k? Okay, so we let n of t, we substitute 5 for t, and then n of t is what? 2 times that, and we solve that. So here we have n of t is equal to n naught e raised to what? K times t. So now when t is equal to 5, this n of t is what? 2 times the initial, and then the initial amount is there, and e raised to what? K times what? Times 5. K times 5. Okay, so this gives us n of n naught e raised to what? 5k, and then 2 times what? That. So we divide both sides by n naught, because that cancels out. Okay, and then we have what? See what I have there. Okay, and then we have, this gives me what? 2 is what? 2 equal to what? E raised to what? 5 what? 5k. All right, so then we take natural log on both sides, is equal to natural log of e raised to what? 5 times k, and the right hand side becomes what? 5k. Okay, 5k e raised to what? E raised, sorry, natural log of that. Let me erase that. Okay, so that gives us, this is what? Natural log of 2 is equal to 5k natural log of e, and we know that is equal to 1. So if we divide by those by 5, okay, it means that our k is equal to what? Natural log of 2 divided by 5, which is approximately to 5 decimal places. Now, I want to warn you, when you find the value of k, leave it at least 5 decimal places, okay? At least 5 decimal places. So so that the difference doesn't, final answer, the difference doesn't become too much of a difference. Sorry. Yeah. Okay. So let's look at it that way. All right. So in this case, my k is that. Then what is the function? The function is, now the function is what? T. Since we know this will be what? N of 0. E raised to what? 0.13, okay, 863 times what? Times t. So this is our function. Now we need it to solve the subsequent parts of the what? Of the problem. Okay, so we have our function as that. Okay, part C. How long will it take for the size of the colony to triple? To triple. Like I said, the time needed, okay, the time needed, let me erase some things there. Okay, the time needed for the size of the colony to triple requires that your n, as n of t, is equal to 3 times your original what? The number, initial amount, or initial number of what? Of the bacteria in the colony. And so we substitute what? 3n for what? N, and get the following. So you get what? 3, just like we solved the part 2, part B, which was 2 n of naught. You get n e raised to, now we know the value of k, so 0.3863 t. Okay, so we want to find what the t is. So we divide both sides by n of n naught. All right, this cancels out. So you get what? 3 is equal to e raised to 0.13863 t. All right, then we take natural log on both sides, which is natural log of 3 is equal to natural log of e, 0.13863 t. And the right hand side becomes 863 t natural log of e. Again, natural log of e is equal to what? Is equal to 1. Okay, so what does that give us? So you get natural log of what? Negative of 3 is equal to that. Then we divide both sides by, so let's write it. Natural log of 3 is equal to 0.13863 times t. Divide both sides by the constant, the coefficient, 13863, and this side 0.13863. Okay, so when we do that, let me write on this side. So you get natural log of 3 is equal to 0.13863. Then divide both sides by 0.13863, and then 0.13863. Now this cancels out. So your t is equal to the natural log of 3 divided by 0.13863. And that's approximately 7.925 to 2 decimal places. So it will take, okay, it will take what? About 7.963 hours. Or if you like, you can put this in terms of hours and some minutes if you want. Okay. So it takes 7 hours and 56 what? Minutes. Now, how do I get this 56? That is 0.925 times what? Times 60 minutes. And that's approximately what? 56. Okay. All right. Then finally, it says that how long will it take for the population to double? How long will it take the population to double? So double the second time. That is what? 4 times. All right. So this is how we can solve it. That's one way. If the population doubles in 5 hours, it would double a second time in 5 more hours. So the total time is what? It is 10 hours. Okay. Or alternatively, all right, okay, you can say that n is what? 4 times the original, and substitute that and solve in the equation. So you have what? 4 n of what? N naught is equal to n naught e, and then 0.13863 t. So again, you use that and solve for what? And solve for t. Okay. Now, if you divide both sides by n, just like we did it for parts B and C, all right, you have what? And you take natural log, you get natural log of 4 equal to 0.13863 t natural log of e. And again, natural log of e is equal to 1. All right, so your t is natural log of 4 divided by 0.13863. Now, this is approximately 9.999 some values, which is equal to what? Is equal to 10 hours. Okay. So that's another way you can look at it. Or you can infer, since we know for 5 hours, okay, it will go to trouble again another what? 5 hours. All right. Now, let's go to the decay. It's the same model, A of t equal to when k is negative. Okay. Again, A naught is the original amount of radiation. Okay. All right. Now we want to define what a half-life is. Half-life is the time required for half of a radioactive substance to decay. And then we use this model in archaeology a lot. In archaeology, where something dated back, they find somebody with the bones, and they want to know when the person died, and possibly what caused the death, and so on and so forth. We use it in a dinosaur and all that to find a number of years. This is how this happens. Okay, so let's take one example. It said traces of burned wood along with ancient stone tools in an archaeological dig were found to contain approximately 2.33% of the original amount of carbon-14. Okay, if the half-life of carbon-14 is 5,730 years, approximately, when was the tree cut and burned? When was the tree cut and burned? Okay, now notice that when you say half-life, that's the main point. Half-life of what? The carbon 14 is this 5,730 years. All right. What it means is that in what? Okay, let us know that this is A of what? A of t, okay, is equal to A naught, and you have e raised to what? K times t. So that means it takes 5,730 years for it, that's a radioactive substance, to decay to what? 1/2 of what? The original amount. Okay, so if that's the case, then we're going to solve for what? A of t. Your A of t is equal to half of what? A naught. Okay, into the formula. All right, so our formula is what? A of t is equal to A naught e raised to what? K times t. Okay, so we use this to find your t is what? 5,730. Okay, your k is unknown. Your A of t is equal to half of what? A naught. Okay, so we substitute that. We have half of A naught is equal to the A naught, that's original amount, e raised to k times 5,000 It is 5,730. All right, I don't know why I'm writing 7,000 instead. So that is 5,730. Okay. And so divide both sides by what? A naught. This will cancel that. All right. So you have what? 1/2 is equal to E. Okay. 5,730 of what? Of K. So again, take natural log on both sides. And this gives us 5,730 E, sorry, natural log of E. Let's take natural log first. So natural log of E raised to what? 5,730 K. Then we simplify the right hand side, which is 5,730 natural log of E, and then equal to natural log of 1/2. Okay. So if you divide both sides by what? There's a T there. I didn't put it there. Sorry, K. K natural log of E. So we divide, this is equal to 1. Natural log of E is equal to 1. So you have what? 5,730. K equal to natural log of 1/2. Then divide both sides by 5,730. 5,730. Okay. So then your K is equal to approximately negative 0.000120968. Okay, then we substitute into the formula. So the A of T becomes A not equal to what? Is equal to that. Okay, the negative came in because of natural log of 1/2. Okay, it's negative. All right, so that's the first part. So this is our model. This is our model. That's the model, is that. So it says that if the amount of A of carbon now present is what? 2.33% of the original amount. Okay, what does it mean? It follows that, okay, it follows that your A of T, all right, is equal to 0.0233 of the original amount. So substitute into the equation and solve. So again, we divide both sides by A naught, that's the original. Okay, that cancels that. So you have 0.0233 equal to E minus 0.000120968T. So take natural log on both sides, just like we've been doing. Okay, natural log on both sides, negative 0.000120968T. Then the right-hand side becomes negative 0. If you use the properties, 0.0120968T, natural log of E. Again, natural log of E is equal to 1. So you have natural log of 0.0233 is equal to that. Then we can divide both sides by what? Negative 0.000120968. Okay, 0.000120968. Okay, this will cancel that. This will cancel out. So therefore your T, okay, your T is equal to natural log of 0.0233 divided by, this is negative though, get by negative 0.000120968. And this is approximately 31077 years. Okay, So the tree was cut and burned about 31,077 years ago. So that's how we can backdate what things that happen. So carbon 14 is one of them, and 12, and so on and so forth. All right. So the half-life of whatever radioactive substance present will be given. All right. So here, this is just information. Newton's law of cooling. We all like coffee. If you put a hot coffee in a coffee mug, and the question is, if you live in the room, how long does it take for it to cool down? Okay, and this is given by this formula. I'm not going to use any do example just to show you. This is a cooling what we use it in physics, and that's a cooling model. All right. So, example, if you have an object is heated at 90 degrees Celsius, and then allowed to cool in the room temperature to 20 degrees. So if the temperature of the object is 95, for example, 75 degrees Celsius, after 5 hours, what is how much of it is cooled down? Okay, so that is the formula. It is K is negative because it's decreasing. Don't forget. All right, it's a decreasing function. All right, and then logistic model. I'm mentioning this because we have been talking about horizontal asymptote. Okay, and I just wanted to see the graph of that. This is a logistic model where A is greater than what is positive, C is also positive, all right, and these are our constants, all right. It is a growth model if B is what is B is the growth rate. If it is negative, it is already negative. If it's positive, then it is what it is. It is growing. It is growth model. If it is negative, it is what it's a decay. All right. So now the graph is what it is. All right. So they have it is bounded above and below. So it doesn't exceed a certain value of y, which is the c, the numerator, which is the numerator. Okay. And then it is decay, logistic decay, and the logistic what growth. So this is just to let you know what kind of other models we have, but we are not going to do example. I have given example here, but I'm not going to solve it, just for your information. All right. So this present the population of yeast in grams after T hours. Can state the carrying capacity and the growth rate, determine the initial population, what is the population after 5 hours, and so on. All right, so that is the end of this section, this video, and I hope I'll see you soon. All right, take care.